Okay, so welcome back to the mini course on semigroup. So we will continue with the study of the abstract category, the category of abstract semigroup. And last time we stopped by showing that the completed version of the semigroup of the sister algebra belongs to the category CU. And now, so the main point of this couple of hours is to show that actually we have a continuous number. Okay. Because it's a functor that is from the category of sister algebra to the category CU, and to sister algebra assign its completed version of the semigroup. And we want to show that this is continuous in the sense that it preserves inductive limits. So to do so, there have been several ways. So probably the first result was to show it in the separable case, and this was done by was for in school. Uh, and in the general case was done by Antoine Pereira deal around 2014, maybe a bit before, a bit later. Okay, the memoirs is published in 18, but it came out in 14, or at least in 16 when I was around. So we will obviously go through the general case, and Ramon already mentioned before, so there is this way to complete a local sister algebra into a sister algebra, which actually will commute with the way to complete the W of A into CU of A. But this technique, which works really well, deals with pre-W semigroup and W semigroup, which are relaxed version of what is a semigroup. And I will present something that is slightly more direct, and it's dealing with what's called pre-Kun semigroup, and this is directly out of what's called domain theory for those who knows. So I will define all these things. So but the idea is the same. Okay, is to deal with a monoid that is slightly relaxed and most of all does not satisfy O1, and we complete it in certain sense to get a CU semigroup. And this actually will be a co-reflection. Okay, so a pre-CU semigroup will be monoid. And actually, these objects will not have an order. Okay, so we kind of forget about the order. We just have a sum. And we have something that is a relaxed version of the compact containment relation. So together with a binary relation, that satisfies certain properties. So it is transitive. with the compact containment relation, and it's positive. Okay, it will certainly not be reflexive. And so in order for the monoid with this binary relation to be a pre-Cuntz semigroup, we ask for some axioms, okay, other theoretic axioms based on this binary relation. So namely, we ask for any elements of the set that we will denote like that. So this is the set of all the elements that are below M for this relation. Okay. We ask that, I mean, there are two equivalent statements, but let's go with the easiest one. We ask that this set admits what's called a cofinal sequence. That is an increasing sequence for this relation. And it's cofinal in this set, in the sense that for any element of this set, you can find an element of the sequence that is covering the element you chose. Okay. And we ask for some compatibility condition as before. So we ask that the binary relation and the sum are compatible. And then we finally ask that the cofinal sequences that we have for any elements are also compatible with the sum. Okay. For any two elements, the monoid, and for any two cofinal sequence of the lower sets, we have that the sum of the sequence you get by summing the two sequences is cofinal in the lower set of the sum of those two elements. In the lower set of the sum of the two elements. Okay, so it's a new language, but if you think of this, when we will be dealing with Cuntz semigroup to be the compact containment relation, it's just a relaxation of O1, O4. So those are the two compatibility conditions from suprema and sum. This is way below and sum. And this is what's sometimes called an interpolation property that will help us to actually be able to construct the completion of such objects. Then we say that M is a free A. So I will write it once. This definition is really taken out of domain theory, so they deal with pre-domain and they have a completion process. And pre-domain is just that you don't have a monoid structure. Okay, you just have a set that has this kind of relaxed version of an order, and then you have a way to complete it. Okay, so and equations into domain are what we are really using here. And we just have to make sure that since we deal with monoids, that actually everything is compatible with the sum. But otherwise, it's really the same thing. So this was pointed out by Kemel in 2014 that there is actually a strong bridge between pre-domain, domain, and pre-semigroup and semigroup. Okay, so now we have defined what is a pre-semigroup, and we want to somehow complete it into a semigroup. So the only thing is, so far we don't have any order, and we know that the compact containment relation is based on the order. So there is a really natural way to do so. Probably I forgot to say what constitutes morphism. So appreciating morphism. Well, this is going to be a monoid map that preserves this binary relation that we have and that satisfies some kind of continuity condition. Because we have seen last time that semigroup are not only monoids, they come equipped with a topology, like order theoretic topology based on the compact containment relation. And O1 is kind of a completion axiom, and O2 is continuity axioms. Okay, so again, all of this is already existing in domain theory. So a pre-CU is a monoid map okay, between two pre-CU monoids, and it satisfies the following. So obviously it has to preserve the auxiliary relation that we have on both sides and a sort of continuity axiom. The continuous here means that for every pair of elements in the domain and the codomain satisfying that the element of the codomain is below the image of the element of the domain, then we can find another element of the domain that is below the original element that will go right in the middle. Okay. So we got it continuous because, again, from domain theory, this is kind of linked to what's called the Scott topology. And the Scott topology is exactly the order theoretic topology we have on semigroup based on the way below compact containment relation. So I don't want to enter too much in detail, but know that there is a well-defined topology, and this is exactly the saying that the pre-image of an open set is again an open set. Okay. So not much mystery here. So a quick remark, obviously, any semigroup is a pre-CU semigroup when forgetting about the order. And defining the auxiliary relation to be the compact containment relation. Okay, so this is it checked. So overall, we get a forgetful functor. I from CU to pre-CU. So for a CU semigroup, you just assign the same monolith, and you only keep track of the compact containment relation. Okay. So the first step towards showing continuity is to study how what's called a completion process. So to complete any pre-CU into a CU semigroup, and we will do this using category theory. So we just want to show that there is a co-reflector. And then to build inductive limits in here is way easier than there. And using the co-reflector, we have an explicit computation of the limit in there by just going to pre-CU and then complete back again. Okay. So probably a theorem and see. So the category CU is a full reflective. Yeah, I was saying co-reflective, but it's reflective, the right termination. Is a full reflective subcategory of pre-CU. Okay. So what does it mean? So there are a couple of characterization of being a full reflective subcategory, and one of them is that so the forgetful functor is kind of the inclusion functor, and this has to admit a left joint. Okay. And this is in turn equivalent to show that any object in pre-CU as a universal completion belonging to CU. Universal in the sense that is compatible with the morphism, and this is what we are going to show. Okay. So So we start with an object here, and we want to end up in a completed object that belongs there. Okay. So a small remark: this is exactly the same process that was done in the original proof, where there is a completion of W of A, the uncompleted or the classical semigroup into its completed version. Okay, so I start with a precise semigroup, and so the way to construct my CU semigroup out of it is to consider the following. So probably notation are not standard, but so I look at the set of all increasing sequence for this binary relation. Okay, so this will come with a natural sum. And I want to define something like a sub-equivalence relation that will give me, when I quotient out, will give me an order compatible with the sum, and such that the way the compact containment relation extracted from the new order is actually corresponding to the auxiliary relation we have. Okay, so uh, it comes with an natural sum. And we consider the following relation, and it's not hard to show that it will be transitive and reflexive. Okay, so the relation will be on this set. Even two elements of here, so auxiliary increasing sequence of M. I say that one is super-equivalent to the other. This exactly means that for any finite stage of the sequence, I can find another finite stage of the bigger sequence that is covering the original one. So for any k, there exists an M such that mk is covered by an L. Okay. So the fact that it's transitive and reflexive is not hard to prove. It's just observing that this is increasing for the relation we have, and that is all. And so whenever we have transitive reflexive relation on a set, we can always antisymmetrize it to get an ordered set. Okay. We will say that two sequences are equivalent if they are both superequivalent to one another. We obtain an ordered set and actually another monoid because we've seen that we already had a natural sum by just component-wise sum, and this will be compatible. Okay, so also this is kind of, I mean, these are all the same argument that we did before for W of A and C of A in the previous classes. So we obtain another monoid. Whenever I take equivalence classes for this equivalence relation, and it's not so hard to show that actually when I extract the containment relation on this, okay, it's also positively ordered because we started with something that was positive. So and okay. So as a matter of fact, so 3 or 4 are not super hard to check, and O1 and O2 it's proofs that we have already seen to show, for example, the existence of Suprema. So I will just make a small sketch of O1 and O2. So O1 is based on the fact that so I want to show that if I take uh, and so I take an increasing sequence in this monoid. Okay, the whole work will be to actually show that okay, can be checked. But it's the same thing as the existence of suprema in the semigroup. Can we say that up to reindexing is necessary? That I, for any, so how am I going to say this? For any k in n, okay, maybe n in n, we can assume that the nth term of the nth sequence is actually covering okay, m n of k for any k smaller than n. Okay. Yeah, it's the process is exactly the same as what Ramon did last time. So you just put all your sequences and you manage going in a diagonal fashion to get bigger and bigger element that switch from one sequence to the next. And once you have that, then you just consider so the sequence given by, so let's call it probably, I don't know, nk is by definition the sequence of just this diagonal sequence, okay? So if you start with random sequences, probably it's not going to be diagonal, but you can always reindex, and I mean, it's the same argument. Uh, so this will be an element in here, and so we can consider its equivalent class, and from construction, it will be a bound for all the elements of my sequence, and it's actually going to be the supremum. Okay, it's going to be the minimal one. Okay. Okay. So one inequality is from construction, and the other one is following again by a diagonal argument. Okay. So in the argument, for one in C or A, those are really the same arguments. And O2 is kind of the same business. So for O2, we can observe the following. So the map from M to this monoid. So it's explicitly defined by taking an element and looking at the equivalence class of its of the cofinal sequence of the lower sets of M. Okay, so where and K is any cofinal sequence in these sets. Okay, so this is the reason why we had the axiom before, and it was kind of the weakened version of O2, and it's defined in a way such that when you look at this quotient thing, you exactly recover O2. Okay, so an explicit construction, and now probably the claim that okay, so let's call this map gamma. So if I take an increasing sequence for my auxiliary relation in M, I can show that so now this is an element in M. Okay, I can get from this element an equivalence class over certain sequence. Okay, so it will be the sequence obtained by, I mean, what I've written there, no? So this is, we can show that actually, so this sequence, so now those are elements in the quotient, okay, gamma and k, and so this is another monoid, and I can show that this actually is a rapidly increasing sequence in this quotient, and it satisfies. So we have shown that these guys, any increasing sequence, have a supremum, and so the supremum of these guys, okay, is in fact supremum is yeah, and the supremum of this is exactly the equivalence class of the original sequence. Okay, so I started with an element here, which is represented by an increasing sequence in M. I mean, auxiliary increasing sequence in M. And for each element of the sequence, I will choose a cofinal sequence. And by a diagonal argument, you can show that this happens. Okay. So how to show this? So it's not super hard. So take this. So if you fix an index in n, so I choose n, k, l, and n, k plus 1, l. So I take two cofinal sequence for two consecutive elements of my sequence mk. And now I just observe that for any index L, I mean, all this sequence will be covered by mk, yeah? And since mk is covered by mk plus 1, and this sequence is cofinal in the lower set of mk plus 1, there will be an index of this sequence that will cover mk, okay? So for any L, I have that mk is covered by mk, and moreover, there exists an index L prime such that mk is covered by n L prime k plus 1. And this is also covered by nk plus 1. Okay, so I've just used the fact that NL, NK, NLK, and NLK plus 1 are cofinal in the lower set of NK and NK plus 1. Okay. And so what we get is that for this sequence, there exists, for all elements of this sequence, there exists a finite stage that is covering all the sequence. And you can show that this is exactly the compact container relation in this quotient. Okay. All index, there exists an index such that, I mean, no, it's the opposite. So there exists an index L prime such that for all L, the element of this cofinal sequence are covered by this guy, okay? And this is equivalent to saying that the equivalence class of uh, this sequence, okay, which is exactly gamma of nk, is way below the equivalence class of this sequence, which is exactly gamma over nk plus 1. Okay. And a similar argument as before shows that so this is a rapidly increasing sequence, and a similar argument show by construction that the equivalence class of nk, so it's a diagonal argument, is the supremum. So we're able to approximate any element here by a time increasing sequence. Okay? Sure. So to any pre-CU semigroup, we have been able to construct a CU semigroup and a map, a pre-CU map from the pre-CU semigroup to the Cuntz semigroup, and it's actually universal. So corollary for any pre-CU semigroup we have constructed, it's what's called its completion. The universal completion will be the object that we have constructed, and the map gamma, so let's call it gamma M, that goes from M to this portion. Okay. In the sense that for any pre-CU map from, for any CU semigroup and any pre-CU map from M to T, okay, there exists a unique map from the condition of M the alpha, this is gamma M, okay, and there exists a unique homomorphism from the completion of M to T such that this couples, okay, so this is the universal part of the corollary, and this is exactly, this is kind of basic category theory, equivalent to saying that the functor has a left adjoint. So this means that home receive from M to T considered as a pre-CU semigroup now is in bijection to the CU morphism from the completion of M into T. Okay. So category theory tells us that whenever you have a okay, so in summary, the U is a full reflective subcategory, and we have constructed the reflector. Okay, so we have the inclusion from CU to PCU, and now we have this gamma completion. Okay, and gamma is a left adjoint for the inclusion. Okay, and now by standard argument in category theory, left adjoint preserve inductive limits. And actually any co-limits. a posteriori limit. From this, we can show that the category CU has inductive limit. And the only thing we are left to show is that actually pre-CU has natural inductive limits. But pre-CU is easier to deal with than CU to construct the limit of an inductive system. And so this is why all this business of completion is really useful. Theorem. So the inductive limit in pre-CU will be kind of an algebraic one, okay? And then upon completion, we get the inductive limit in CU of the system, okay? So a posteriori, U as inductive limit. And okay. And for any inductive system in CU, we have that the limit in CU of the system, okay, is isomorphic to the completion of the limit in pre-CU of the same system. Okay, so I will make the effort to write I of SI and I of sigma J. Okay, so I apply a forgetful functor to each of the object endomorphism of the system. I get an inductive system in pre-CU. I compute these limits in the following way I will show you now. And then the limit, you complete it with the above process and you get the limit of CU. Okay, so this is, again, coming from really standard category theory about reflectors and full reflectives of categories. Okay, so for this theorem, the second part is shown by this reflector gamma. And so the only thing we are left to show is that pre-CU has inductive limits. So I take my I take the derivative system. Okay, and as I said before, the limit is kind of algebraic one. So we consider M to be the disjunct union up to, I mean, some equivalence relation where Mi in Mi and Mj in Mj are equivalent. This is by definition whenever there exists a bigger stage of the system where they agree. Okay, such that mu I k m I is mu j k m j. Okay. I mean, whenever you consider algebraic limits, it's the way to do so. Okay, so you just um, identify any element of the system whenever they actually match on a further stage. And so usually this is compatible with the sum, and we will only have to preoccupy to take care of this auxiliary relation. Okay, and we so and we and with so a sum given by mi in mi plus mj in mj is just um, okay, blah 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 blah. So I will just send both of them in a further stage, a further common stage, and I will make the sum there. So mu ik over mi plus mu jk over mj, where a is an index that is further away from I and j. Okay, so and then an auxiliary relation given by, and we do the same thing. So an equivalence class is covered by another one whenever there exists k further away from I and j, such that mi in this further place is covered by mj in this further place. Okay, so what it says is that whenever I have two elements, I can send them in a common place, and if there one is covering the other, then I say that the equivalence class is covered by the other equivalence class. Okay, so everything is really algebraic here. There is not much mystery. One has to check that this is well defined and this is compatible and so on and so forth, but everything happens at the finite stage. So everything will just unravel from the fact that all the guys that we have in the system are actually pre-CU semigroups. Wait. It's being signed on another device, blah, blah, blah. Allow, I guess.
Oh, absolutely.
I think we have lost the meeting noise here. Okay.
Someone trying to log in, I think.
Yeah, I think I gave him authorization. Okay. So probably it's a good place to make a small break before entering the continuity. So again, the fact that this M was equipped with this sum and this binary relation is a pre-CU semigroup is kind of easy to check because everything is happening at a finite stage. Okay. So yeah, let's take 5-minute break. Then Okay, so welcome back to the second part of the session. So we will continue towards the proof of the continuity of the functor CU. So we have done the first step to show that the category CU had inductive limits, and we have kind of an explicit computation and an explicit way to to build them, and this is gonna be useful for the proof of the continuity. Okay, so theorem. So I could probably, even though I already said it, but which is, I guess, the whole point of the completed version in Elliott Ibanescu was to actually build an invariant that was suitable for system algebra, because as Ramon said earlier, many of the system algebra can be built out of uh, inductive systems. Okay, so proof of this, we start with an inductive system of system algebra. Okay, so we have several objects to consider. So we want to show that the limit in CU of these guys is isomorphic to CU of the inductive limit of these guys. Yeah. So this is what it means to preserve inductive limit. So we will slightly fix some notation. So SI will be conveniently the CU of AI, and observe that the pre-CU semigroup associated to this cool semigroup also uh, we will use both SI for the pre-cool semigroup and the semigroup associated to CU of AI to avoid. Now alpha ij, this is gonna be this morphism, and also this morphism too. Okay. And now we write alpha. Okay. So this is the system limit of our system. And we will take similarly alpha I to be okay. So let's make a nice diagram that will be useful for the rest of the proof. So I have a psi, a j, and so I will write m. I will explain who is m. I can complete m with gamma, get gamma m, and then here I have cu of a. Probably write it here. Okay, so those maps are okay, so with my notation, alpha ij is here. I have alpha a here and alpha j there. Okay, I just apply the CU functor. Probably I will explain with m. M is just the pre-CU limit of Si alpha ij. Okay. So this we built it in an explicit way. So observe that Cu of A as a pre-Cu semigroup does not have any order, right? It's just a monoid with this auxiliary relation, but now the auxiliary relation is given by the compact containment. Okay. Mark Si as a pre-Cu semigroup is Cu of Ai with the sum and the compact containment relation. Okay. So I have a bunch of pre-Cu semigroups with like a really concrete auxiliary relation, which is the compact containment relation. I can build their limits in an algebraic fashion, and then I can complete this limit, and I know that this limit is the Cu limit of the Cu system, okay? From the reflection properties that I showed earlier. And so blah, blah, blah. And so we have this object there that is obtained by taking the semigroup of these limits. So we have the object and a bunch of morphism. And it's not hard to show that it's a co-cone for the inductive system in Cu. And what I want to show is that actually those two things are isomorphic. Okay. So let me fix some notation here. I will write this will be sigma I, and this will be sigma j. So sigma I, by definition, is the composition of gamma with it. Okay, actually, it's m and yeah, what's the amount of names? Beta definition. Okay. Okay, so I have whenever I compute the limits, it's a co-cone. So I get an object and a bunch of maps from each finite object into the limit that I call beta I. So beta I are pre-Cu morphisms, and whenever I compose with gamma, I obtain a Cu morphism. Okay, which actually are the limit morphism from Sj to the Cu limit. Okay, so this belongs to Cu. So observation gamma m. Okay, so we have m beta I is by construction the pre-Cu limit of the system, and gamma m, right, and sigma I is the CU limit of the system. Okay, so far I haven't done anything if not compute those two limits. And by the universal property of the inductive limits, I have to map. No? Here there exists a unique beta that make this diagram commute in pre-CU, and I also have a unique W such that this diagram commute in CU. Okay, so beta is in pre-CU and W is in CU. Okay, universality of the limit. Okay, because CU of A and alpha and all the maps alpha I, alpha J are a cocon in both categories in pre-CU and CU. So yeah, so everything commutes here in my diagram. So what I want to show, or what is enough actually, is to show that this W is an exhaustive map. I know it's a CU morphism, so I just have to show that it's bijective, and I will be done. Okay, so we start with subjectivity, probably. Prove the subjectivity. I mean, I will do basic technique from set theory. So I take an element here and I define the preimage. So before I need the following plane. The plane states that for any two elements in CU of A, then one is compactly contained in the other. Okay, I can find okay, an element in a finite state that is gonna stick in the middle. Okay, so again, this is a sort of interpolation property that we've seen before. Uh, so proof. Uh, yeah. So using O2, we can assume that A prime, yeah, we can assume that A prime is equivalent to a cut down of A for some epsilon. And even if it's not, you just take a cut down that is, such that A prime is compactly contained in the cut down, and you just write A prime to be the new A prime. Okay, so this is not much mystery. And okay, in the C-star world, the nice thing is we can always approximate any element of the limit as close as we want by an element in the final stage. Okay, so so we choose a B in some finite stage. Okay, I need to go to stabilization, but I could do. Let's just assume that A prime and A are in the algebra, and makes things easier, but it's the same argument. So I can choose a positive element in some finite stage, is that the image of B in A is really close to A. Yeah. Okay, probably I need a finer tuning of this. But this is an element in A, and I choose a B such that its image in the limit is really close to that one. So we know that whenever two elements are close to one another, I can cut down any of the two by epsilon over 4, and it will be Cuntz below the other one. So this has been shown by Francesc. So we get that the cut down of this element by epsilon over 4 is Cuntz below B. By the image of B in the limit, and similarly by J of B cut down by epsilon over 4. Okay. But this overall is just a cut down by functional calculus. It's just this cut down. And okay. So I do get now, by cutting down both sides somehow, functional calculus, I can show that probably we need functional calculus and Rodam's lemma. And this can be the same. And so overall we get that This cut down of A is below the cut down of the image of B. So this will be my, yeah, probably C. And here, C. So this cut down of B is C, and C goes below this thing. I mean, phi j of C, which is what we wanted. Okay. Probably I don't want to erase this thing. Okay, we remember the claim. For any two elements that one is completely contained in the other, I can find an element at the finite states that interpolates those two things. So now I got an element in here, and I want to find a pre-image in gamma of M. So what I will do is I will interpolate and then go up there. And since everything commutes, I will be able to build a sequence, like a rapidly increasing sequence of gamma M, whose supremum will be my A here. So by O2 in CU of A, I can find this rapidly increasing sequence whose supremum is my element. And now I will just interpolate any of those guys by elements of the finite stage. Okay, so find for each K, find CK in some finite state JK. I mean, probably you will have to go to stabilization, but it's just a small detail. And you can choose always that the finite state you choose is always increasing. Such that the following happens. So I have xk is compactly contained in alpha j, the class of ck, compactly contained in xk plus 1. Okay. So since those two increasing sequences in CU of A are interpolating one another, we get that the supremum are equal. So supremum of alpha j ck in J is the supremum of xk, and this is A. Okay. So I have found a rapidly increasing sequence that converts to my elements, but this rapidly increasing sequence is all of the terms are coming from a finite stage. So I can just use this diagram. Instead of sending them directly to CU of A, I can just primarily send them to gamma of M and then come back down to CU of A. This is commutative. Okay. So what I'm saying now is that I have a rapidly increasing sequence in gamma m whose, such that its image is rapidly increasing in CU of A, and the supremum is the target that we wanted to hit. Yeah. So let me write this down quickly. Alpha j of C, or this is actually j k, right? Sorry. Okay. Yes, no? Yes. Alpha j k of C k. So going from SJK to CU of A, I can just pass by gamma of M. Is actually sigma j composed with W of CK. Okay, so sigma j, so I have an element here, and I send it through gamma m through sigma j, and then come back down, and I get the same thing. Okay, and all of these are CU morphisms, so it preserves suprema, compact containment, and so on. So what I'm saying is now so A is the soup of this alpha jk ck, but now using this thing is the soup of this CU morphism applied to the ck over k. And now since this is in CU, I can just switch suprema and the morphism. So this is omega of suprema sigma jk of ck. And this is CU semigroup, because now this lives in gamma m, so it has a suprema, and this belongs to gamma m, and is the element that we were looking for. Okay, so I do get that A has a pre-image in gamma m. Okay, so surjectivity is done. So we have surjectivity here. Now let's show injectivity. So that injectivity, we will use the fact that this map from M to gamma M so when we did the proof of the completion, we show this fact that this is the explicit pre-CU morphism. Where MK is any star cofinal, auxiliary cofinal sequence in this thing. And for any okay, now I'm low on notation for any ML gamma of NL is increasing. I mean, it's rapidly increasing towards gamma I. Okay, so this is something we've shown earlier, and we need another claim stating that for two elements in a finite state, positive element, again, stays true for stabilization, such that their image in A compared for the Cuntz equivalence in some sense. So I have two elements in my sister algebra at a finite stage. I send them in the limits, and one is Cuntz below the other. Then for any cut down of A, there is a finite stage that the cut down of A is actually Cuntz below. So this is saying that this relation may not happen at the finite stage, but if I take any cut down, then I can make it happen in a finite stage. Okay. Overall is what I'm saying. For any epsilon positive, there exists a finite stage such that this Cuntz equivalence happen in AK. Okay. So the claim together with this property of the completion will give us the injectivity, and we will be done. So proof of the claim. So I know, okay, so I fix an epsilon. There exists an element in A such that the compression of Pj of B by x star is really close to Pj of A in A. Okay, so this is by the definition of Cuntz equivalent. And since I can approximate any element of A by an element of a finite stage, I will approximate X by someone in some finite stage that is bigger than J. A K such that the K of R is really close to X in A also. Okay. So when I put these two together, what it gives me is that the K of R, the J of B, the K of R star is really close up to an epsilon to the J of A. Okay. Still in A, but now we know that star homomorphism are of norm 1. So this will be useful because, and also they preserve multiplication and the star operation. So being star homes, we can conclude that phi R, phi J, K, B, R star is really close to vk a in this further stage. Okay. And so this proves the claim, proves the claim. Okay. Okay, but now that we know that whenever two elements compare here for the Cuntz superequivalence, we can actually compare them in the final stage. It's gonna be the same business. Then we can kind of factorize through the upper thing. So if I have two elements in there that go to the same image, or let's show that it's an order embedding. It will be equivalent in the place. So probably I can erase this bit. No? So to show it's an order embedding, I start with two elements in gamma of m. So this will be represented by increasing sequence, auxiliary increasing sequence in m. So I take two of those sequences. Okay, this will give me elements of gamma m, and I assume that their image through W are compared with the order. Okay, so assume that W of the equivalence class of Sk is smaller than the image of Tk. Okay, so what I want to show now is that the equivalence class of Sk is smaller than the equivalence class of Tk, which is by definition showing that Sk, the sequence Sk is subequivalent to the sequence Tk for the equivalence that we constructed, namely that for any k, for any element in Sk, I can find an element TL that is covering Sk. Okay, this is, all of these things are the same. But the good thing is, I have the commutativity of the big diagram. I can rewrite this thing to be, okay, now I need to use this fact. Where is it? Yeah, this fact. So I star I can rewrite this inequality to be, so I know this thing can be written as a supremum of some guys, and those guys are exactly the gamma of each element of the sequence. Okay, using what I wrote here. And now this is a star home, so I put the supremum out. So I get that the supremum of W composed with gamma of Sk is smaller than the supremum over K of W composed with gamma of TK. Okay, so I'm nearly there. Probably I keep the claim, but I'm going to use it. Again, up. So this inequality exactly means that for any K, there exists an L such that W composed with gamma of Sk is smaller than W composed with gamma of the L. Okay. And okay, I can even make something stronger because this is star increasing and this preserves the way below, so I can choose it to be compactly contained. And we've seen that using this claim, you can show that this is equivalent to saying that Sk is in M is covered by Tl. Okay, so yeah, probably is not straightforward. So maybe it is. Okay, so this composition of W with gamma is beta, no? So it's beta of Sk is well below beta of Tl, and yeah, and Sk, okay, now take representative of Sk and Tl, so Sk is blah, blah, blah. And the L is some ZL. So this is in Sk, this is in Sl. Okay, so they are representative of those. The element of M are equivalence classes of some element of the finite stages. And okay, so saying this by commutativity is the same as saying that okay, exactly. So alpha K of Zk is compactly containing alpha L of ZL. But now those guys are exactly Kuntz classes of positive elements, right? So this, by definition, is the same as saying that Cu of, okay, phi k of, well, there are a lot of equivalence classes, but AK is the L of AL, and AK and AL are representative of those Kuntz class, ZK and ZL. So we have overall two positive elements coming from a finite stage that not only, it's even stronger than this hypothesis. And Okay, so using the claim, that for any epsilon, yeah, for any epsilon, ek, ak, epsilon, which is compactly containing I, yeah, vk, I'm running out of indices. vk, L is already taken, no? vk, p, P of AL in ALP. Okay. But now, once we have this, we just send them back to gamma m, and since those are CU morphism, we obtain that for any epsilon, we have so sigma, yeah, sigma j of sigma k of sk is f of k. And this is what I wanted, I guess. Okay, so the proof is dealing with a lot of indices and so on, but the idea is pretty clear. It's based on this claim and how we construct the limits. So yes. So I started with those two sequences, and is it what I want? I'm a bit lost. No, it's not what I want. Oh, okay, right. So yeah, I want them to compare in n. So this is, since they compare at a finite state, this is exactly saying that sk is I mean, I even have more than that, but okay. And this is saying that okay, so recall that this was for a fixed k, there exists an L, so this means that the sequence sk is subequivalent to the sequence TL, and this is the same as saying that sk is this. Now, so I studied with two equivalence classes of sequences that such that their image compare in CU of A, and I proved that actually those sequences compared in the first place. Okay, so now I think it's correct. So W is a CU isomorphism, and we get that CU of A is actually the limit of the SIs. Okay. So I have no more time, so probably it's a good place to stop. So see you next Tuesday, and we will go on with some example and application of Cuntz semigroups.